piecewise functions. You've pretty much done stuff that's more complicated in Desmos, and some of you have taken this totally over the top in Desmos. What you were graphing was piecewise relations, when you could limit the domain or range and actually draw only part of that function or part of that relation. Some of you used relations, which are any relationship not necessarily passing the vertical line test. So let's actually look at the general idea, and I want to show you the symbolism that you'll see in maths because it doesn't always look like just what Desmos did. Okay, so the general idea is that piecewise functions are defined, or piecewise defined functions are exactly what they sound like, functions that are defined in pieces, and the non-overlapping part is what makes them a function. And here's when you worked with Desmos and limited the domain and range, you were graphing, you were creating piecewise relations. And for some of you, they were rather complex piecewise relations. A piecewise function is only different from a piecewise relation in that a function passes the VLT. That's a non-overlapping part. So let's look at the symbols and how this works when you will see them down the road. So here's the first example that we have a function defined in two pieces. The top piece is just x squared plus 1, but it's only limited to where x is less than 0, not less than or equal to, just less than 0. And the second piece is y equals, or the function equals x minus 1 for x greater than or equal to 0. So let's start by finding evaluations of f at -2, f at 0, and f at 1. So if I want to plug in, I'm basically plugging in a -2 for x. I need to first establish which part I go to, and where, if I'm looking at x as -2, I want to be in the first part. So I plug in a -2, so I can say f at -2 equals -2 squared plus 1, and find that value for plus 1 is 5. Find that value when x is -2, y is 5. So next is -2, y is 5. So we're up here, right here. That is a point on the function. So go ahead, try the other values. So here's the plotting of the first point. When I plugged in an x of -2, I got y of 5. So there's -2, 5. When I plug in a 0, I get -1. There's that point right there, 0, -1. I plotted it. F at 1, and I thought, okay, if I plug a 1 in, this 1 qualifies to be in this interval, so 1 minus 1 is 0, and there's that point right there. So this is how I establish individual points that fit into the piecewise function. So now let's actually graph this. So I want to graph y equals x squared plus 1, but only where x is less than 0. So sometimes it's easier to plot the whole thing and then just erase the part that you don't want to be part of the piecewise function. And then the same thing down here. So see if you can sketch a graph of this. Pause the video, sketch a graph, and then come back to see how I did. So I got the left-hand side of the parabola. Notice the open hole there. That's important. That maintains its status as a function. There's exactly one place to plug in an x value. So notice the domain is just listed here. This is the domain, which is ultimately all real numbers. There's going to be a place to plug in any single x I want. My range is all real numbers greater than or equal to -1. Okay, let's look at something else. You can put these on your calculator in the following way. So you want to divide by the set of values you want to include. So it explains how to use this in the test function, but let me show you on your calculator. Actually, let's start with my y equals. This is what it ultimately is going to look like on your calculator. And then the question is, how do you get those less than signs? It's under the test function. So you can see where the test is by pressing second math. So I'm going to do that right now. Second math, and I can see there's oh, what did I push? I pushed the wrong thing. Second math, and there, phew. Okay, there I get my equals to, not equals to, greater than or equal to. I get that whole. So I can actually pull up these inequalities. So let's go to y equals, and you can see how I'm dividing by, and I'm establishing what the domain is. If it doesn't fit there, it's the equivalent of dividing by a false, as is explained in the text, or dividing by 0, which you can't do. So when we graph this, I'm going to press graph. If you have a different window, you might want to press zoom 6. well, why don't I do that? Zoom 6, zoom standard, and it will graph for me. You'll notice I use different colors. So you'll see the first is in, what does that look like? Blue. And then the second is in green. It looks like it's really light. Maybe it'll darken up a little bit. But I've got two different colors. Notice that open hole doesn't show up very well at all, in fact. So you have to really know that that's excluded. So here's another example. Let's graph this. They're actually easy to graph by hand. You might have an easier time graphing it by hand than on your calculator. Some of you might use Desmos, and it's like, yeah, sure, use Desmos, but no, you will not have Desmos on a standardized exam, or you will not have Desmos on your AP exam, should you choose to take that in a couple years. So it'd be really good to figure out how to use your calculator or figure out how to do that on your own without the use of Desmos. I'm going to show it to you in pieces. I'm going to graph it for you in pieces. Here's the first. If I wanted to graph y equals x squared plus 3, you know this as an open parabola, opening upwards parabola at 0, 3 of a vertex. And then if I plug in this endpoint -2, I can figure out exactly where this is, and that point is at -2, 7. And then I only want to draw that little part on the left-hand side. That's where x is less than -2. So the rest of the parabola I can ax out. So that makes it a little easier to see exactly what's going on there that's part of a parabola. Now, y equals 7 is going to be a little bit easier to draw in this interval. So go ahead, try that one. That's it, just a horizontal line. You'll notice this was an open hole in the first, but I'm going to fill it in here. It's the same point, notice. I'm going to fill it in here. I'm trying to fill it in. It looks like it's not filled in, but I think it's just reflecting. That should be filled in. And then it stays horizontal until the point 1, 7. Now for the second, it's a line. So start by plugging in a 4. Start by plugging in 4 to see exactly where that is. And then you can plug in one more point, and then you have the equation of, or you have the graph of that line. Plug in a 4, you get a 7. And then you can either plug in a 5 and get the value for 5, 9, and graph that line from 2 points, or you can use the slope of 2, up 2 over 1. So then you've got the two pieces. Now what's interesting about this one is the domain. There's values that are excluded for x. So there is no x value between, actually greater than 1 and less than or equal to 4. So that's excluded from the domain. So let's establish what the domain is, and then let's plug in these values. Started with, okay, domain, started overachieving, stated the range. Okay, and then plug in a 0. 0, you just need to see where it's going to fit in. It's going to fit here. 0 is between -2 and 1, and so the result is just 7. What's interesting is that g of 3 is undefined. G of 3 does not exist. You could also, instead of writing undefined, you can write does not exist. So I'll put that, does not exist, g of 3. Here's a third example. It's a little bit trickier because you need to remember what the parent function is. Here it's 1 over x, and it's been shifted 6 to the left. Okay, here this is the absolute value function. It's the v. It's moved 2 to the left and 3 up. Do you see that? 2 to the left and 3 up. And this is a square root function, the half a parabola. It's shifted down by 2. So now we've taken these three functions. You only want to take pieces of them, and these are the pieces. See if you can graph this by hand. If you want to use your calculator to help you out, or if you want to use Desmos to help you out, that's fine. But see if you can graph this by hand, get an accurate rendition on this chart. A little bit more complicated. If you forgot your parent functions, I've kind of put a key to what the parent functions are here. Okay, and then I plugged in values here to find out what these values are. Here's the absolute value. Notice the open holes everywhere. This is 1 over x. It looks kind of funky. It's like this. And then this is the half of a parabola, only in this one little region. Fourth and last example, try this on your own, use whatever you want. Notice that examples 3 and example 4 are a little bit harder than what you're going to see for homework tonight. So if you feel comfortable with 3 and 4, I think you're good to go. So go ahead, try and graph this. Use your calculator to help you if you want, or use Desmos. And here's a graph of the 3 pieces where I've got the endpoints, the values of the endpoints marked. If you want to know how to find them, you can just take a -3 and plug it in there and know that it's going to need to be an open hole. If you can plug in a -6, know that that's going to be an open hole as well. and so forth. So I hope this came out okay for you. This one does look a little bit tricky. This is this kind of shape, but it's only this little piece of it. For homework tonight, since I printed it out, I've changed it. So these are the problems. Pre-cal text, page 60, 65, and then page 107 and 109.